Hi, everyone. Good morning. My name is Mark Carrera. I am the chair for this session at DataWorks, and welcome to the best session at DataWorks. Glad you're all here. So we'll start off today with Dr. Steve Movit and team talking about operational representative data and cybersecurity for avionics. So Steve is a member of the staff here at IDA, focusing on aircraft survivability, including cyber. And he recently set up a cyber lab for both the DOT staff and IDA folks to play around in. And I believe this work comes from some of that. So, Steve, take it away.
Okay, my name is Steve Movit. And my esteemed colleagues from our lab are on the author line there. Justice Clutter and Connor Trask are also going to be speaking. Justice has a doctorate in physics from the University of Illinois, and he's been here for about 14 years. And then Connor was our most recent summer associate, and now a research associate at IDA. And he has a bachelor's in mechanical engineering from Michigan State, and I have my doctorate from Penn State in Astrophysics. But now we all do cybersecurity as part of our job. And so this talk here is talking about gathering operationally representative data for avionics cybersecurity. As Mark said, basically we started with a lab that was supposed to be for teaching and training. We realized we had some research quality simulators and some research quality ideas. And we've expanded on it, and we'll present it here to you today. So the overarching problem with aircraft is that their networks are designed for assured message delivery. When you want the flaps to move, when you want your landing gear to go down, you don't want that to be a maybe. That has to happen. And so if you use protocol like Ethernet, you might lose packets, you might have fragmented packets, and so that's not the way these networks are designed. And also these networks, these aircraft networks, they're quite old, and they really haven't been updated in terms of security or in terms of authentication. And so if you want to zoom out, the avionics industry, general aviation especially, there's physical security is what you rely on. And if you look, for instance, many of you are familiar with the TSA from when you fly at the airport, but the general aviation and civil aviation is not nearly as locked down. What you find out is that the regulations are limited, and the security requirements are vague. You're basically required to have a restricted area, and that restricted area requires a badge, and that badge must have your picture on it. But beyond that, there really aren't very many requirements. And so airport security is a problem. And then that doesn't even account for any upstream vulnerabilities that might happen. Because even if the aircraft is secure, the manufacturer's site may not, the aircraft may be in transport, et cetera. So again, there's these insecure communication standards on our aircraft, on all of our aircraft. They were designed for reliability. For instance, the MIL standard 1553 has, every MIL standard 1553 bus has redundant wires. It has an A bus and a B bus in case one of the wires break. The remote terminals and the bus controller, the systems that communicate on the bus can kick right over to that backup bus and keep operating so that if you're in the air, you don't have any safety issues, you're not losing any critical systems. So I mentioned MIL standard 1553. One of the other most prevalent standards would be your ARINC 429. ARINC stands for Aeronautical Radio Incorporated. It is a nonprofit company that sets these standards. And if you look at these two standards, you look in the academic literature, there are known attack vectors for MIL standard 1553, and the references are there. And they could be exploited by rogue devices because when you're on a 1553 bus, if you're electrically connected to the network, then you are trusted. There is 100% trust. You hear a lot about zero trust these days, but these aircraft networks have 100% trust, and the messages are not encrypted. There's similar vectors that you could use on an ARINC 429 bus. I'll talk about why ARINC 429 isn't quite so prevalent in the literature. 1553 is sort of, the big shiny object. But again, these are all connected to very, very important systems on the aircraft, flight control systems, flight critical systems. And they have no authentication and no encryption. And again, 1553, you can plug right in. So we built our own avionics simulator. This is not ours. This is an Army intrusion detection system, and it's actually Ethernet. But we have created hardware-in-the-loop simulators. Our first one is complete. We have others in work. And we just first built these simulators for training, as was alluded to by Mark. But there's research to be done here. So we have these full pilot-in-the-loop, hardware-in-the-loop simulators, which can demonstrate a cyber attack with mission effects. They can collect operationally realistic and relevant bus data. So a lot of the literature is done with simulators, with circuit cards that create these messages. One of the main examples, they randomized all the ARINC 429 messages to make sure they sent all the possible labels and messages that one could send, but that's not operationally realistic. It just covers the space. And three, if we were to test out intrusion detection algorithms, we can use our simulators as a test bed for that because we have the real hardware. And then the flight simulation program provides very realistic GPS and aircraft attitude data. So real quickly, I'll describe the protocol before my colleagues jump in. ARINC 429 is very interesting. It is very unique and not the sort of network that you tend to think about. So right now there's thousands of planes flying with ARINC 429. It is ubiquitous. And the standard was first published almost 50 years ago, and there have not been any security updates. So when new types of avionics come out, they'll update the list of labels in which you could possibly be sending messages from what types of systems, but it is still inherently insecure. It lacks encryption, it lacks authentication. So ARINC is, unlike the 1553 bus that I talked about, that's sort of like a party line telephone where everyone can hear. This is a very, very small network architecture. So you have one sender and then up to 20 receive nodes. And it is unidirectional. It is just one avionics system sending to others. If you want to talk back to the original sender, you have to build another ARINC 429 bus. So your aircraft can have many, many ARINC 429 buses, and they don't take up very much space because they're so limited in scope. And this is why people tend not to think of it as much of a target as they would 1553, because the 1553, again, you have all of your avionics talking to one bus controller, whereas this is limited in scope. However, very, very flight critical systems can be connected to ARINC 429. And it also served as an excellent proof of concept for our hardware in the loop demonstrators, because we could just get in between two systems and attack from there. Okay, so now Justice is going to take over.
All right, good morning, everybody. So Steve's done a great job kind of laying out what the problem is and what we have to deal with. And I'm going to take some time and get you more familiar with our hardware in the loop simulator from a hardware perspective. So can everyone hear me through this? Perfect. So what we did is we set out to generate this hardware in the loop simulator so that we can explore this ARINC 429 bus. Our HITL mimics an aircraft that is dependent on the 429 bus. And specifically, we look at the ARINC 429 connections between an enhanced ground proximity warning system and the multifunction display. We really wanted to create a proof of concept for what we're doing. Even though we're focusing on this EGIPWIS to MFD connection, I want to highlight that the attack that we want to demonstrate today can be extended to other avionics systems, as Steve was highlighting before. So in order to generate an environment that the pilot can interact with and that can actually drive all the other avionics components, we use the X-Plane software running on a PC. And then we also have generated the necessary Python code in order to allow all of the environment that's generated from X-Plane to propagate out to the various avionics hardware components. Let's see, there we go. So this is a simplified diagram of our HITL. As I've indicated before, we have a minimum amount of components to highlight the effect that we're looking for. Right, so I'm going to go through each one of these individual pieces and show you how this works. So the first thing we have is a PC running X-Plane, okay? And this is where the pilot's going to sit, and this is, as I mentioned before, also going to do all the communication about position and environment to all of the other avionics components. From PC1 over on the left-hand side, the data moves down to the Egyptus, which was the Enhanced Ground Proximity Warning System. And this is an image of that Egyptus avionics component here on the right-hand side. And the only thing that's really going to the Egyptus is position, and that's done over RS-232. The data then also comes out of the Egyptus and goes to the multifunction display. Here we have a Garmin GMX200, which is acting as the role of our multifunction display. The diagram doesn't really show, but we have two different types of data coming to this. We have the ARINC 708 message data, which is actually the display raster data that comes, and we also have ARINC 429 messages that come across from the Egyptus unit. So that is the HITL as you would see it in a normal general aviation aircraft. Okay, what I have not shown in here is any kind of adversarial components, which would be the elements of a cyber attack. And so now I can highlight what those additional components might look like for somebody. So everything in this red box is what I would call the adversary. Here we have a PC, which acts as a leave-behind device. And that device here talks to what we call an ALTA-DT, and this is a component which which creates ARINC 429 message traffic, essentially, right? So that data is then going to, and I should highlight, this is what the ALTA-DT looks like. That data then moves over to a relay. So the relay is what allows the adversary to switch between actual message traffic from the Egyptus unit to false positive data from the adversary to go to the multifunction display, which might impair the pilot's ability to safely fly the aircraft. So let me walk you through the anatomy of an attack as I've kind of alluded to it in my images there. So number one, we're going to record legitimate alarm messages from an Egyptus unit. So we have taken our simulator, our HITL, and we have put it into a bad state, so forth, a dangerous state, and we've actually taken the data from the Egyptus and we've recorded that on our leave-behind device. Number two, we create this leave-behind device, and we somehow get that into the aircraft, okay, and that can take over that ARINC 429 bus and play those messages. And that was actually three, I guess. 2 and 3 are combined there. Now, I should highlight, this could also be as a supply chain attack. So we're talking about somebody who's going to get out on the flight line or in one of those maintenance spaces and potentially put that device in. But it could also happen upstream somewhere. And then finally, we execute a denial of service attack or DOS attack on the pilot's avionics display by taking over that 429 bus and transmitting those messages. And this attack impacts the pilot's ability to maintain his or her situational awareness because they don't have those avionics systems that they might rely on available to them. So, and this could result in the loss of a mission goal or, possibly the aircraft or loss of life. So, so now what I'm going to do is I'm going to turn this over to Connor Trask, and he is going to show a video demonstration of our HITL. I would like to highlight we will have our HITL available upstairs during the poster session tonight between 5 and 7. If you guys are interested, please come by and take a look at it. We'd love to share it with you. So, yes.
So, yeah. All good. We'll just skip over that one and get straight to the video. So, again, we'll have live demo where you can actually get hands-on with the simulator at the poster session. But for ease of presentation here, we just have a pre-recorded video. And all right, so we're doing voiceover then. We're doing it live. As you can see, this is the scenario that we have set up. We are flying a Cessna, I believe, on approach to DCA through what is very clearly instrument flight rules conditions, right? We're navigating using our multifunction display because there is absolutely no way that we are going to be able to see any sort of landmarks in this cloud cover. We're using our altimeter and our airspeed gauges to ensure that we're, staying on a solid approach at a reasonable altitude. And so when we're in a situation like this, where we are, completely in instrument flight rules conditions, sort of at the whim of our instruments, being able to trust those instruments and, trust that they're giving us accurate, timely data is really important. And so, if something were to happen that could compromise one of those instruments, such as, in this case, we're not looking at the artificial horizon, but that's obviously very important in this scenario as well. So, if something were to compromise one of these devices and cause it to potentially start malfunctioning, as you now see here. So what we're doing now is we are sending terrain warning messages to the multifunction display. And what that does is it makes the multifunction display think, oh my God, you're about to crash into terrain. I have to show you the terrain map so you can see what you're about to hit. But if you look at the actual terrain map, there's no terrain on it. That's because, we're still at a safe altitude. We're not actually about to hit anything. But because the device is receiving these messages, it keeps trying to flick over even when I hit the button to go back towards the navigational map. So because we're constantly bombarding the multifunction display with these terrain warning messages, we have this denial of service attack where you're no longer able to use your navigational map because every time you click over to the navigational map, it clicks you back to the terrain warning map, which, as you can see here, really doesn't contain any useful navigational information for where you are in relationship to the runway. So this is a demonstration of what the attack looks like. Hopefully, now that I've scared you a little bit from flying on planes, we can get into mitigations and how we address these sorts of attacks. So as Steve mentioned, there's an incredible absence in the publicly available literature on these sorts of ARINC 429 attacks. The only paper we were able to find is this hardware fingerprinting for the ARINC 429 avionics bus from Gilboa, Markovich, and Wool. And they detailed a method for intrusion detection on ARINC 429. So we're not, strictly speaking, preventing these attacks, but we're looking at a way that we could detect when something like this has occurred. So their work builds on previous work implementing these intrusion detection systems, or IDSs, in similar unsecured buses such as CAN buses, which is what you get in most of your automotive systems. You may have seen, news stories about people hijacking cars and, causing the accelerator to floor. That's CAN bus, which is a similar sort of system. The really important thing with ARINC 429 that they identified in their paper is that the strategy for detecting these adversarial messages has to be message agnostic. There's no encryption or authentication in this standard, so you can't use the message content itself to detect whether that's a valid or invalid message. So what their approach is, as you can see from that one image in the top right, is they segmented the ARINC 429 message into segments. So you have low segments, null segments, and then transition segments, between each of your sort of plateau sections. Then what they could do is they could train an intrusion detection system on these segments and the electrical characteristics of them, and then use that to identify whether a transmitter was the valid transmitter that we had trained our detector on or some new transmitter connected to the network. And they tested detection of both rogue transmitters on the network and rogue receivers on the network. So a couple of notable achievements from this work. They did demonstrate that they could successfully identify rogue transmitters and rogue receivers on this network. So much so, they had such resolution in their detection that they could actually identify different devices from the same manufacturer. So just slight manufacturing differences would create notable enough electrical differences that they could detect that with their algorithm. Additionally, transmitter attacks were detected within 50 milliseconds because they're sort of more obvious, whereas receiver attacks were detected within 3 seconds, which is still quite good for a detection time. There were some really key limitations in their paper, though. As previously touched on, their messages were created by integrated circuit boards, which you can actually see their setup on this previous slide. Great for doing sort of initial testing, but certainly not operationally realistic. In a similar vein, their message content, as Steve alluded to, was not operationally realistic. They sort of were trying to cover the entire space of messages, but all the messages they actually tested were of odd parity, so an odd number of ones in it. And the ARINC standard specifically says all messages must be even parity. So the messages they were training on wasn't even operationally realistic. And then finally, they weren't evaluating the sensitivity of these voltage characteristics to external factors such as temperature or degradation over time. So our work doesn't seek to address that last concern because our lab isn't currently set up for it, but we do seek to replicate their results in avionics hardware with operationally representative messages. So our initial results on that front, we collected and then segmented the data from 3 transmitters. We have our one valid transmitter, which is the Ojibwas, and then 2 malicious transmitters, the Alta DT, as you saw previously, and the RTX ARINC to serial port interface. So what you can see on the left there is the actual data from a low to null signal transition from each of these 3 transmitters. So you can see just visually, the RTX is a very sharp rise, the Alta DT has a very slow rise, and then our valid Ojibwas is somewhere in between the 2. Now, it's important to note that while we can sort of visually extract this information, and perhaps one could train, a classifier just on this, the paper took this segmenting approach, and so we wanted to follow through in their segmenting approach and see, well, can we also see differences in their high segments? Visually, all 3 of these high segments look relatively constant, which makes sense because these are the values that are dictated by the standard that you have to reach, a certain high value and a certain low value. However, if we do PCA, principal component analysis, on these high segments, which again was done in the paper, you can see that these segment level differences really start to sort of separate themselves out once we've collapsed them down into this 2-dimensional space. And then finally, they chose local outlier factor as their anomaly detection algorithm. There's a number of reasons that are detailed in the literature for why this is a good anomaly detection algorithm, but it achieves really promising results using only a small section of that high message. So just the sort of first initial rise can really tell you a lot about where this message came from. So just quickly going over some future work we aim to get to, expanding the number of avionics systems included in our HITLs. This includes expanding to other buses, such as MIL Standard 1553. This also lets us investigate system-level cyber attacks, where maybe we compromise multiple devices simultaneously, or we explore potential for lateral movement across different types of avionics buses. Always looking to expand the number of operationally realistic messages that we have in our data set, and then finally develop and testing this intrusion detection system in real time, so really operationalizing it. So in conclusion, these are critical avionics buses that are really vulnerable to cyber attack. These cyber attacks can be conducted with publicly commercially available tools, and all the information that was done to do this was, publicly available. It was Wikipedia and public standards. As a result, though, because these attacks are feasible, cybersecurity testing of these buses is also very feasible. We've demonstrated an operationally realistic mission effect here, so there's certainly motivation to go and test it as well. We've assembled this sort of data set of operationally realistic bus traffic, which certainly testing on aircraft is ideal, but this data set we have right now is better than simulated data at the very least. And there are relatively simple techniques that we can use to distinguish these rogue adversarial devices from our valid sort of baseline device. So with that, are there any questions? Yes?
If you go back to slide 20.
This one?
Yeah, this one.
Sure.
So you've color-coded the different transmitters here, but if you just had the data, does your device distinguish between the RTX and the valid transmitter? They look like, visually, if those weren't color-coded, they look hard to distinguish.
Yeah, so I think the important thing about this is that because we've done PCA, what we've essentially done is taken our time series vector of voltage readings, which is about 1,000 entries long, and we've compressed that down into 2 dimensions. So the PCA in 2 dimensions makes them look relatively similar. However, the actual local outlier factor algorithm that we use to detect whether it's the same or not has an accuracy of 0.996, I believe. And certainly there's ways you can get even higher accuracy if you want.
Since it is segmented by the one transmitter, 20 receivers, how vulnerable are systems on ARINC 429 to other attack pathways? Like 1553, since it ties the whole aircraft together, you can use a maintenance loader or any number of other ways to get to a fairly critical system. Other than the stay-behind device, how vulnerable would 429 be to some other attack path?
So, I mean, I think you hit the nail on the head. A lot of these systems talk over multiple buses, so you would probably want to do some sort of combined movement. You could move to a relatively critical system over another network, and then do an attack over 429. It's sort of your end game. So that would be the other way to get to something very, very critical that was on the 420 that was only connected via 429. So does that answer your question?
Sort of. I guess other than a stay-behind device, how would you do the attack? Without getting too specific. Obviously.
So you could also compromise the software in one of your transmitters.
One Zoom question. Question is for Connor. Connor, did you all consider analyzing characteristics that may be present in the noise of the different transmitters to isolate good and malicious transmitters?
I guess my question to that would be what noise exactly they're talking about. Are they saying if they have like different noise signatures or?
So this is Brian Conway. I will get the two of you together and you can chat offline.
Okay.
I mean,
Yeah.
The one point is that aircraft power is really, really dirty and awful, and this is, lab power. It's a power supply. It's from, it's a mail order power supply off the shelf. It's not fantastic, but it's not aircraft power. So that is a really good point. I don't think anyone's ever looked at real aircraft data and run this analysis. It'd be a great extension.
And I will just highlight one methodological thing that we did do. You can see here the oscilloscope. This diagram is actually slightly inaccurate. The measurements we took from the oscilloscope are actually between the relay and multifunction device. So we are taking our measurements at the same location for all of these transmitters. So really we made sure that what we were capturing was differences between the transmitters and not differences in the impedance of the wire at a given point in our circuit.
Okay, well, let's thank our speakers again.